LiDAR is being used for all sorts of interesting use cases. In this video, we're actually going to cover how LiDAR is being used to map natural disasters and aid researchers in monitoring and understanding rock slides and other interesting natural disasters. We will explore the difference between aerial and drone LiDAR data, and what are the advantages of having on-demand, high-density point clouds. And as a rare treat, stick around to the end and we'll show you how you can get your hands on these data sets and look at this stuff firsthand.
So, hey, Mike, welcome to the show here, and really appreciate you coming to join us here. For our viewers, would you mind telling everybody what NERI is and what you guys do?
Yeah, my name's Dr. Michael Grillo. I'm a senior research scientist at the University of Washington and the manager of the Rapid facility. I interface with researchers interested in working with the Rapid facility at all stages of their proposals.
Hi, I'm Karen Dudinsky, and I'm the Rapid data scientist, and I help facility users process and share their data.
My name is Andrew Lida. I am an operations engineer for the Rapid facility. I manage the facility's equipment and help manage projects both in the office and out in the field.
Amazing. So you're the tech behind the show. I love that. So what is NERI and what actually does it do?
So the Rapid facility, it's actually not an acronym. Everybody thinks it is. It doesn't stand for anything.
Okay.
The Rapid facility is part of what the National Science Foundation created and what they call the Natural Hazards Engineering Research Infrastructure. It's a bit of a mouthful, but the NERI network, it's a collection of institutions, universities around the country that do exactly what's in the name. They do engineering research for natural hazards. It might be like wildfire testing on structures, wind tunnel testing, there's shake tables, there's simulation centers, wave tanks. It's a large network, and the Rapid facility is the field reconnaissance arm of this. So after a natural disaster, the Rapid facility will support researchers going into the field and collecting data on natural disasters.
Amazing. So how does LiDAR fit into this? And particularly, how does drone LiDAR fit into this?
LiDAR is one of the tools that we use to collect these perishable data sets. And they're perishable because after a natural disaster, after a hazard, things move quite rapidly, especially with the cleanup and the recovery phases. So we want to make sure that we get in as soon as possible. But we're researchers. We are not first responders. So we always make sure that we are entering a zone after the first responders' rescue, life-saving recovery efforts are complete. But we'll come in as soon as we can after that to capture the scene. And a lot of times what the researchers need is a digital twin, that 3D information, because it might take all day to survey a single building and take measurements and all the precise information that they need for their research. But with LiDAR, we can capture that information, not just on like a single building, but even a broader area very quickly. So that's really the way that LiDAR enables us to capture this data. It's that snapshot in time, and it allows us to capture it much more quickly over a broader area. So we use ground-based laser scanners, handheld mobile laser scanners, and airborne LiDAR with our Phoenix MiniRanger system to do that.
Amazing. And then Andrew, why the MiniRanger? Why do we want to use that?
So the MiniRanger for us has been kind of a pre-built system that we can easily deploy to the field, and the quality, and it's easily adaptable to different environments. Since the Rapid facility typically deploys to a post-disaster environment, we need something that has a good size, factor, weight, is maneuverable, something that we can ship out and take into a post-disaster environment. And so the MiniRanger has been great for that. And we can really deploy it quickly and gather with the MiniRanger research kind of quality LiDAR data from the air in really hard to reach areas or in areas that pose a little bit of a challenge for a more traditional survey type of data collection. And then subsequently, we get a really good temporal data set that we can use for research, or then we can use to help train other researchers and help the broader NERI and NSF community.
And then, Michael, can we talk about like a particular case that you guys may have deployed to?
Definitely. Yeah, we've used the MiniRanger in a number of different deployments, mostly landslides. So one of our primary uses for the MiniRanger actually came up in late 2020, kind of the height of the pandemic. There was a landslide in Haines, Alaska.
Okay.
Dr. Margaret Darrow from the University of Alaska Fairbanks contacted us and said, hey, I'm really interested in capturing this landslide because it was a very extreme rain event, and she was interested in understanding the mechanisms of failure and contacted us asking, I'm going to apply to the National Science Foundation for some funding, and how am I going to collect this data? She's like, what's the best way to do this? Because like I mentioned before, we have terrestrial laser scanners, which we've used to monitor landslides before. We have all sorts of drones to do structure from motion, 3D point cloud generation. But for her case, what she was specifically interested in trying to look through the vegetation, LiDAR was the tool. And this slide was particularly dangerous to traverse, so terrestrial laser scanning wasn't really an option because we can't actually get out onto the slide as much as we would like. And there was almost 900 meters, was it 900 meters? 900 feet.
I don't know that.
I think it was.
It sounds about right.
I forget exactly how tall it was. Yeah, it was because it was about 1 kilometer to the top of the slide. So it was almost 1 kilometer from where we would have to collect the data. So we needed a drone to be able to get upslope. So LiDAR data and using the drone to capture that LiDAR data was really our only option. So we discussed options with her because there are airborne LiDAR options like fixed wing and helicopter platforms. But what she was interested in looking at some of the rocks, the cracks and the faulting, and especially the detail of the headscarp at the top of the slope. The airborne LiDAR data just wasn't going to supply the point density and the detail that she needed.
And you were saying that they had historical aerial data from an aircraft before. I think this is important for people to see the difference between, aircraft aerial LiDAR and what you guys had brought out to the island.
Haines, Alaska is north of Juneau. It's just west-southwest of Skagway. It's about a 3-hour ferry ride to get up to Juneau. It's only accessible either via a ferry flying in, or you have to drive through Canada to get there.
So that whole terrain is pretty steep.
Yes, quite remote. So the slide I'm showing right here, this is the right after the slide occurred. The DGGS, the Department of Geologic Services for Alaska, wanted to fly this slide, the Beach Road landslide, in the entire area because there were dozens of landslides after this rain event in December of 2020.
Okay.
You can see in this image, these are some cross sections of the slide looking up the slope, and there's almost a sort of double vision effect that's going on. It's a little blurry, and when we spoke to the folks who collected this data, they said, yeah, it was actually gale force winds when we were collecting this because this occurred in winter, and winters in Alaska can be pretty harsh. and they said, we needed to collect this. This was the only time to do it. So this was the data set that they got. And unfortunately, there was just so much wind and the airplane was moving so much that the individual flight lines just do not match well. So the data that they collected, it's definitely still usable in these discrete areas, but we had to separate out a single flight line, which for Margaret's purposes, because like I mentioned before, she really needed the ground points and stripping away the vegetation and just looking at the terrain model. So looking at a single flight line just wouldn't do it for us in this case.
Yeah, you can see the strip mismatches all the way up through that.
Yeah.
Okay.
So this is the top, the head scarp of the landslide, and we're going to be looking at a profile right here where this from to it's 170 meters across. Just showing the comparison between what we collected and that 2020 flight, and this kind of underscores why this is necessary. So the red points are the MiniRanger points that we collected with our platform, and the green points are the airborne LiDAR, that single flight line. You can see on the slide itself, it's fairly dense. It did a pretty decent job covering all that. It's a little sparse over here, but certainly in the dense vegetation on the right and the left side, you can see that the ground points are almost non-existent.
Right.
The LiDAR data, it's just, and again, this being a single flight line and understanding that, but we can't fit them together to do any change detection because there was so much noise. So we just had to look at this one.
Right. And for our viewers, that's an apple to apple comparison, because you had aerial data that had strip mismatch. You really couldn't use that. So for comparisons, we had to use a single swath of aerial and a single swath of drone to make this kind of comparison.
Yeah. So in this case, Margaret needed that high density on the ground so she can look at the faulting and the fracturing. And the MiniRanger system, the drone system, is really what provided this. So to actually do the comparisons, here's another slide that kind of underscores the point density from that single flight line. You can see on the slide in the highest density areas around 55 points per square meter. Once you get outside of the slide, and this is cropped, but you can still see a little bit on the fringes of the slide. There are a number of areas that are just black where there's no data at all, or there might be 1 or 2 points. So the point density drops dramatically.
Once you get into the vegetation.
You can see these lines of density, where the aircraft is pitching forward and down or up and down. As opposed to the MiniRanger data set that we collected, we focused our investigation on the scarp, which is why it's the highest density area. And these are ground points only, and that's close to 800 points per square meter. And when you get outside of that into the vegetation, it does drop down into the light blue and the dark blue area, but we're especially around in the head scarp, there's still up sometimes 300 points per square meter. So I don't know what the average is for all of it, but even if there's 15, 20 points per square meter outside of the slide, that gave her the resolution needed to look at some of the bedrock fracturing and make a comparison to the 2014 LiDAR data. The 2014 LiDAR data, which happened pre-slide, is the only pre-slide LiDAR data that we have for this area. So we had to use this kind of as our baseline for volumetric comparisons. And it wasn't too bad. This is ground point density. For 2014, the slide happened right about here. And you can see it's, maximum 13 points per square meter. In some areas that's black, but it kind of goes down to maybe 3 points per square meter. But for the volumetrics, that was...
Well, and really quick for our viewers, as we go from slide to slide, this color scale is changing, where the last slide we looked at, we're up to 300, 400 points per meter squared. Now we're talking into, what does that say, 15?
It's 13 is the max.
13 is the max. So So even though the colors are the same, they don't communicate the same amount of point density.
Right. You can see this is the road. This is the beach road running through on the right hand side right here. This is actually this house. You can see the little L. That's this house right here. So the beach road slide.
Barely missed it. Well, thank you for sharing that. Now, Andrew, you're the one that actually flew that out there. So, what was the advantages of bringing the MiniRanger out there, and what were some of your challenges?
Yeah, so actually, it was both Mike and I were out there flying the landslide. So,
I don't want to steal it. That's good.
So we went up there with the MiniRanger. It was, as Mike discussed, it was a bit of a challenge to get up to Haines, get the equipment there. Involved planes, ferries, cars, pretty much every mode of transportation you can get all the equipment to the site.
Right.
The site, the landslide had occurred in winter under heavy rain, snow, and so we actually had to wait till the summer till we could actually get to the site. And then that summer we got up there. We were able to access it via the beach road there.
Mm-hmm.
Could pull the cars up there and set up kind of a mobile launch area for the drone itself. And from there we could access the entirety of the site with the drone and all of our equipment.
Gotcha.
And so it presented a bunch of challenges to get there and to get up. The actual elevation change of the landslide itself presented some challenges to make sure we had the correct terrain following for the drone system, to make sure we were getting fairly consistent altitudes to the landslide. But the aerial LiDAR system really did present the best possible solution for that, so we could keep that consistent distance to the landslide, but also we can get multiple different viewpoints of the landslide and surrounding terrain, so we could hit the near vertical fault scarp or landslide scarp that was at the top of the landslide. We could hit that, and that's near vertical, but we could still hit that with a LiDAR.
Right.
And then going down the landslide, it undulates, so you have multiple different angles or slope angles of this landslide. We can hit that with a LiDAR with multiple flight patterns going over it, and we can get really dense returns on the whole entirety of the landslide, and that was really good for us. And do all of that safely from the beach road and with very little actual people on the landslide. So there was little danger to ourselves as well. And so in the end, we were able to get a really good 3D kind of geo-coordinated data set of the landslide that you saw Mike showing. And we were even able to return a year later and do it all over again so that we could monitor the different changes of the landslide through time with erosion, settling, and movement of the landslide as it continued, because it hadn't quite stopped moving, as landslides do.
Yeah.
So we've, with all the safety on there, we were able to get all of that and provide a really good research data set for Margaret Dare there at University of Alaska Fairbanks and her team. So.
And then, how did you know that you got everything?
Well, first off, Margaret said good job to us, so in the field, right, we can kind of see as the data is coming in, and I would say close to real time, unless we're really far out.
Right.
But then at the end of the day, whether we saw it real time or not, we can bring the drone in to wherever we're seeing. We can download the data fairly quickly off the drone itself, off the LiDAR unit, and take it into one of the Phoenix's Spatial Explorer there on site.
Yeah.
Now, it's not going to have full accuracy with all the GPS and the full processing, but we were able to bring in all the flights and just kind of overlay them on top of each other so that we can see, okay, we got all the area we wanted to cover, or we were up there for usually 2 to 3 days to cover everything we wanted.
Right.
And so, in day one, we could look at, okay, looks like we got the bottom of the landslide really well. Tomorrow, we were going to fly at the top, but let's make sure we hit the landslide scarp really well, and we can focus on that the next day. And so we were able to do that at end of the day, and then afterwards we can bring all the data back to here at the Rapid facility, and process the data into like the really accurate geo-coordinated result that we can use for research or presenting to the public and stuff like that.
Karen, where is this stuff stored at, and how can they get access to this?
So part of our mission as a facility is to make natural hazard research data publicly available for all users. So we host it on the Design Safe Cyber infrastructure, and that is also funded by the National Science Foundation, and that's a platform for data storage and analysis. And all this data is at no cost to users because we want to encourage reuse and further development of research. And going to that website, so this is the main Design Safe website, and you do not need an account to access the publicly available data. But with this, if you go to the Publish tab on the left-hand side, you can see all the data from the different facilities within the NERI network published. And then if you want to refine the search just to rapid, you can put the keyword rapid in, and then with these are all publicly available, and you can go in and explore the data. And then another great tool that Design Safe has is this application called HazMapper. And this is a web-based application to geospatially visualize and explore data sets. So this is the one we have up for the Haynes landslide. And just for context of the area that we were talking about before, it's down right here in relation to Alaska. And then when you zoom in, this blue box is a point cloud data set for the aerial LiDAR. And if you click on the blue point cloud, a pop-up appears with a preview of the data set and some basic metadata of the file. And we can actually further explore this data set when you click this view button. And it brings up this really neat viewer where you can further explore the data. So for example, you can increase the point budget to help some visualization appearances of the data set. And you can also go in and do some basic clipping functions. So if you wanted to just highlight the certain area for the landslide, you can use the clipping tool and then drag the box and highlight the features within. And then there's also some really great measuring tools. So before talking about the distance of the landslide, and you can just have the point and approximate about 715 meters from the profile side. And it's really great because you can zoom in and see the detail from the Phoenix MiniRanger, and you can see the actual tree trunks and the slope.
Wow, you can really convey, what happened there. It's a lot of resolution. Nice job,
and all
guys.
you need is an internet access, so it is very accessible to all users to be able to look at this data set.
Okay. That's a great job. Very nice. Wow, guys, I really appreciate you showing me this. I mean, this is really, at least for me, cutting edge stuff, and it's such a good purpose. The other thing I want to ask you guys is, this is Phoenix's 10-year anniversary. And, in that 10 years, we're always asking, how was your experience with Phoenix? And is there anything you guys would like to say with them?
Andrew, I'll let you go first.
All right. Well, to Phoenix, thank you for all the help with some of our data collection if we ever needed, whenever we contacted you. And really for the system itself, it's been very rugged and extremely useful for the Rapid facility. And so we are now on, I think we've had, you can call it 2 systems. We originally got in 2018 and upgraded in 2021. And so we hope to continue using Phoenix LiDAR systems as we go forward.
Yeah, I think I'll just echo those comments because we've, like Andrew mentioned, we've had this instrument since late 2018, I believe, and it's a workhorse. It's still going strong, and like we have upgraded the IMU and the CPU, but it's still the Regal Minivux 1, which is a fantastic scanner. I know they're not selling it. They've moved on to the 3 or the 4 now, I think. But
Right.
it's really great, and it's definitely one of the features that we have here at the Rapid facility. So I'd say thank you, Phoenix, for building such a robust tool, and we're really excited for all the advancements that you're going to be making in the future.
Amazing. That's great. So the last question I have, or not question, but I more want to talk about, you know, I've been selling LiDAR for a number of years and dealt with a lot of universities, and so has Phoenix. And one of the struggles that a lot of researchers have is getting access to this kind of technology. Whether it's someone doing their research grant, or somebody's trying to do a particular project or augment or even validate that this is what they want to do in their study. So for those folks that are seeing what you guys are doing, and since you are supporting this large infrastructure of researchers, is the field work to validate all these studies along the way, since you are their field collection arm for a lot of this stuff, how would people get a hold of you if they wanted to consult with you, or even research, using your equipment through your branch there?
Yeah, I would direct them directly to our website, which
Okay.
we put the link down below. You'll find all the information about the Rapid facility. We are funded by the National Science Foundation, so we do prioritize NSF-funded projects. But we are open to working with all researchers, not just natural hazards necessarily. So we do have, in the past, we've worked on some other projects. So I say, please send us an email, reach out to us, check the website, and we'll see if if it's non-NSF project funded, then we'll try and do what we can. We'll see if we can work with you. But if you are NSF funded, then definitely reach out, and we'll support your research in any way that we can.
Amazing. Well, Michael and Andrew and Karen, thank you so much for sharing. I mean, this is an amazing amount of knowledge. At least I've learned a lot, and I'm sure our viewers have. And so thank you for sharing this with us. This was amazing.
Yeah, it was a pleasure. Thanks so much for the opportunity.
Thank
All
you.
right.
Yeah,
Thank
thanks.
you.